Hello, today we're going to look at dark matter and galaxy rotation, and we'll be looking at the reasons for thinking that there might be a thing called dark matter. In my video Gravitational Fields, A-Level Physics, I showed that if you have a planet, let's say, orbiting the Sun, here's the planet, here's the Sun, and the planet is orbiting with orbital speed v, I showed that the centripetal force, which is keeping that planet in circular motion, is mv squared over r. I know that planets actually describe an ellipse, but for all practical purposes we can regard them as circular, and therefore we can derive this equation for centripetal force, which keeps the planet in circular orbit. And that force is provided by the gravitational force, and that we said was G, which is the gravitational constant, times capital M, which is the mass of the Sun, times little m, which is the mass of the planet, divided by r squared, where r is the distance between the Sun and the planet. And so the centripetal force is equal to the gravitational force. And you will see that the little m's cancel, and if you rearrange the formula you will find that v squared is equal to gm over r, g capital M over r. And if you look at that you'll find that g of course is a constant, it's the gravitational constant, m is a constant, it's the constant mass of the Sun, and that gives you the conclusion that v squared, the velocity of a planet, the orbital velocity of a planet, is proportional to 1 over r. So as r increases, v squared decreases, and consequently v decreases. So the further away a planet is from the Sun, the smaller is its orbital velocity. In passing, we can just say that this leads on to Kepler's third law, because if you think about the time it takes for a planet to do one complete revolution, that time, t, will be the distance that it travels, which of course is 2 pi r, one complete revolution is 2 pi r, divided by the speed, which is v. But we know that v squared is gm over r, so if we square this equation here we get t squared is 4 pi squared r squared over v squared, and if we substitute v squared here we get that that is 4 pi squared r squared over v squared, which we now know is gm over r, so that r now becomes r cubed. 4 pi over gm is a constant because they are all constants, and that leads us to what is essentially Kepler's third law, which is that t squared, the time that it takes for one planet to perform one complete revolution, is proportional to r cubed, the distance away from the Sun. But let's return to this formula here. V squared is gm over r, so v squared is proportional to 1 over r. And let's look at what the implications of that are for planets orbiting the Sun. If we take a graph showing v, the velocity, the orbital velocity of any given planet, and r, the distance from the Sun, then you will find that the relationship is given by this formula here, and that will look something like this. And I'm not plotting these to scale, but essentially that would be Pluto, that would be Neptune, that would be Uranus, that would be Saturn, that would be Jupiter, that would be Mars, that would be Earth, that would be Venus, and that would be Mercury. Not to scale obviously, but essentially the further out you go, the lower is the orbital velocity. If we just do a little think experiment for a moment and consider what would happen if you were to orbit inside the Sun. Of course, that's not a practical proposition, but let's draw, there's the Sun. And let's suppose that we've got a planet inside the Sun. As I say, this is a thought experiment. What would govern the speed of that planet? The answer is, of course, that the formula still applies. V squared equals gm over r. G doesn't change, but the mass does, because, as we've seen from previous experiments, the only mass that will be relevant for a planet orbiting inside the Sun, I repeat, it's a thought experiment, is the mass enclosed within the orbit. All the mass outside the orbit actually cancels out. And so you've got a smaller mass. And so once you get inside the Sun, this picture does not continue. It doesn't continue going up. Indeed, if the orbit were exactly at the centre of the Sun, the velocity would be zero. And what you therefore find is that the pattern would look something like this. As soon as you get inside the Sun, that's this section here, actually the velocities start to fall again until at the centre of the Sun, the velocity is zero. So that's the pattern of planets orbiting the Sun. The further out you are, the slower the velocity. If you could have a planet orbiting inside the Sun, that also would have a lower velocity as it got towards the centre of the Sun. That, of course, is impossible for the purposes of the Sun, but I draw it because of the next stage of the argument we're about to move on to. So let's move on to galaxy rotation, and let's consider a galaxy of stars, and let's consider a star somewhere in that galaxy, and we'll give it an orbital speed v. In other words, it is orbiting around the centre of the galaxy with speed v. Now, you might think that on the basis of what we've just looked at, if you were to plot the velocity of the star, the orbital velocity, against the distance from the centre of the galaxy, then you would see a graph that looks like this. In other words, exactly the same as that. The further out you go as far as the stars are concerned, the slower the velocity will be. And if you get very close to the centre of the galaxy, then the velocity will also decline. That is what you would expect on exactly the same argument as we derived for this graph here for the solar system. But in fact, if you observe stars in the galaxy, what you find is that this bit is okay, but then you get a line like this. In other words, the velocity remains unchanged no matter how far out you travel. This is what you would expect from the formula we have derived above. This is what you actually see as far as the galaxies are concerned. The velocities of stars are independent of the distance from the centre of the galaxy. Now, what does that mean if we go back to our formula here? Well, we have derived that v squared, the velocity squared, is equal to the gravitational constant times the mass, when we were looking at the solar system, we were looking at the mass of the Sun, divided by r. And if v squared is a constant, that means that this is a constant. Well, we know that g is constant, and that means that m divided by r must also be constant. So for this graph here, we are saying that m divided by r is a constant in order for the velocity to be a constant. But what is m? Well, m is the mass contained within the orbit of any given star. Now, at first sight, you might think, oh, well, that's perfectly easy to understand, because obviously, the further out in the galaxy you go, the more stars there are going to be within the orbit of that particular star, and therefore the more mass there is going to be within the orbit of that particular star. And so obviously as radius increases, in other words, as you go further out from the centre of the galaxy, so the total mass within the orbit will increase because there are more stars within the orbit, and therefore it's perfectly reasonable to suppose that the mass contained within the orbit of the star divided by the radius, that is the distance from the centre of the galaxy, will remain a constant. But in fact that doesn't explain it. If you get right to the edge of a galaxy, then as you move out to the furthest most stars, the mass contained within the orbit barely changes at all. And so you'd certainly expect, even if it were true, which it isn't, but if it were true for the inner stars, you would certainly expect that by the time you got to the outer stars, where the amount of mass is barely changing at all, you would expect that the stars' velocities would begin to slow down. But even at the far edges of the galaxy, the velocities are staying the same. So actually that is not, you can't account for that by assuming that the mass is increasing in proportion to the distance from the centre of the galaxy. And there's a serious problem with this graph here which shows that the velocity does not change, because if that were really true, if the velocity of outer stars were as great as it is measured to be, those stars do not have enough centripetal force to maintain them in orbit, purely based on the gravitational formula that we've derived. So these stars should simply fly off into outer space. It should not be possible for the galaxy to keep them in orbit because there isn't enough gravitational force from the mass of the stars that we observe. And so we draw the conclusion that the mass of the galaxy must be greater than the observed mass appears to be based on the stars that we see in the galaxy. Now there are ways of determining the mass of a galaxy based on the observation of the stars, but there's also a system called gravitational lensing. And this is really a feature of general relativity. It says that if you take any object, I'm going to consider this is a galaxy, but it could be any massive object, and you take a photon of light that just skims the edge of that massive object, it will in fact be diverted. That's a feature of general relativity, and you'll see why that happens if you look at my video on general relativity. Now we can explain why this happens using Newtonian mechanics. You actually need to involve general relativity as well, but let's start off with Newtonian solution, and we'll consider a massive object of radius r, and here's the photon of light skimming the surface and being diverted through an angle alpha. This means that a photon travelling at velocity c, the speed of light, has been diverted with a velocity delta v in that direction. And if the photon's velocity has been changed, then it must have been subject to an acceleration. And in Newtonian mechanics, we can identify what that acceleration is, because we can say the gravitational force, which is the mass times acceleration, is also equal to the gravitational constant times the mass of the large object divided by the mass of the small object over r squared. The m's cancel, and that gives you an acceleration of gm over r squared. Now a change in velocity is equal to the acceleration, which we just determined, times the change in time. What is the change in time? Well, for practical purposes, we're going to say that the gravitational impact of this massive object is at its maximum as the photon travels this distance here. And that distance, of course, is 2r. It's twice the radius. It's the circumference of the object. There will be some gravitational attraction, obviously, on either side, but the main attraction will be when it's very close to the object concerned. And it's travelling at speed c, so how long does it take to travel this distance 2r? The time, delta t, to travel that distance is obviously the distance divided by the time, which is 2r divided by c. And so we can now say that delta v is the acceleration, which we've just shown is gm over r squared, times delta t, which we just showed was 2r over c. And that gives us, one of the r's cancels out, that gives us that the change in velocity is 2mg over rc. And now we can draw the vector diagram, which is basically this shape up here. This is the speed c, this is the change in velocity delta v, so let's draw that. This is the speed c vector, this is delta v, and delta v is 2mg over rc. And if this is a small angle, alpha, then you can say that alpha is equal to 2mg over rc squared. In other words, it is this distance divided by this distance. And you can see that alpha is indeed going to be a very small angle because g is a very small number and c squared is a very big number, and that's in the denominator. So g and c squared will combine to produce a very small value for alpha. So you need very good equipment to be able to detect that angle. Now, I did say that this formula was derived using Newtonian mechanics, and that in fact you have to use relativistic, general relativity. And if you do, amazingly you find that the correct answer is just twice this. It's actually 4mg over rc squared. That is the formula once you've applied the principles of general relativity. So in a peculiar way, you find that the general relativity solution is simply double what you get from the Newtonian solution. But that's the one that needs to be used. But it doesn't really matter, it's still a very, very small angle. However, if you measure that angle, then 4g over c squared is a constant. You know the values of those. You can observe the radius of the object that you're looking at, the galaxy, whatever it may be, and therefore you can deduce the total mass of the galaxy. And what people have found is that the mass that you deduce from this gravitational lensing approach is much greater than the mass that you deduce if you try and work out what the mass of a galaxy is purely on the basis of the number of stars within that galaxy. And so we reach the conclusion that a galaxy must contain matter that we cannot see. And it can't all be accumulated in the middle, otherwise the velocities of the outer stars would fall off as the distance from the centre increased, just as planets' velocities fall off as the distance from the sun increases. In fact, the matter must be spread throughout the galaxy, possibly in the form of what's called halos. And it's that matter that we cannot see that has been given the name dark matter. But what is it? Well, one argument says that there isn't any dark matter at all. The problem lies, so some people will claim, with the concept of Newtonian mechanics. You see, we say that the force between two bodies of mass m, capital M and little m, is g, the gravitational constant, times m divided by r squared. But what happens if it isn't actually r squared? Suppose it's almost r squared, but not quite. Suppose we have assumed it's r squared simply because, for all practical purposes, that works within our ability to measure. But suppose actually r squared at huge distances isn't quite the right formula. Well, if that were the case, then that would, or could, explain why we observe stars in galaxies behaving as they do. And that is called the modified version of Newtonian gravity, sometimes called MOND. Another argument says that the mass in the galaxy that we cannot see is accounted for by neutrinos. There are, of course, billions and billions of neutrinos being created in stars all the time, and maybe these somehow coalesce to form mass. The mass of a neutrino is not known. It's a very, very, very small mass, much smaller than that of an electron, if indeed it has a mass at all. But if it has a mass, albeit very small, if you've got billions and billions and billions of them, they could create a massive mass, and possibly it's neutrinos that account for the additional mass inside a galaxy. Then there are those who argue that this additional mass could be accounted for by what are called MACHOs, that is, massive compact halo objects. These could be black holes, or maybe they could be what are called brown dwarf stars. That's maybe stars that have given off all their energy and are no longer emitting light. Or maybe stars that coalesced to become a star but never quite had enough mass for the first nuclear reactions to take place. So they never became bright, and they are sitting scattered throughout the galaxy, adding to the mass, but not in any way that makes them visible. And then there's the argument that the dark matter is made up of what's called WIMPs. That is, weakly interacting massive particles. This assumes that there are particles that we haven't yet detected that will be massive particles, probably heavier than the Higgs, which is the reason we've never been able to detect them so far, that have peculiar properties that mean that we are not able to detect them, but which are present in galaxies in huge amounts of mass. To give you some idea, it is generally reckoned that of all the matter in the universe, 83% of it is dark matter, and only 17% of it is the matter that we would recognise as such. There is a further explanation for this additional matter, or if you like, additional gravitational pull, and that is the idea of parallel universes. In the theory of general relativity, there are additional dimensions, but those are dimensions that we cannot see or understand. And that means that there can be another universe, a parallel universe, in a dimension that we can't see. So if we depict our universe as a flat universe, like that, with our stars and our galaxies in that universe, there could be another universe straight above it, a parallel universe, also with stars. We can't see that universe or in any way interact with it or experience it, except that its gravitational effect will impact on our universe. So possibly it's that accounts for some of the supposedly additional matter in galaxies. You may also hear of people talking about hot dark matter and cold dark matter. The difference being nothing to do with temperature. Hot dark matter means that particles are travelling at relativistic speeds, that is, very close to the speed of light. Cold dark matter means that the particles travel much more slowly, and in order to get galaxies and stars to form, you need cold dark matter, otherwise the particles are travelling too quickly for the material to coalesce to form the structure that we see in galaxies and stars. But just exactly what dark matter is, and indeed whether it exists at all, we have yet to discover. Finally, I should just perhaps say that dark matter is not the same as dark energy. These are both things that have yet to be found, but are assumed to exist, but they are two completely different things and are intended to cover two quite different circumstances. Dark matter has been developed to explain what I've explained in this video, the reason why stars' velocities in galaxies are as they are is because the galaxy must be more massive than it appears to be, and because we cannot see the matter that is in the galaxies, we call that dark matter. Dark energy is used to account for the fact that although the universe is expanding, if the only long-term force acting on the universe were gravity, then you would expect that expansion to slow down as gravity acting on all the objects in the universe starts to slow them. But what it is currently now thought is that the expansion of the universe is accelerating, getting faster. And if that's the case, there must be some kind of negative gravity at work. And that is the idea of dark energy, on which I shall make a separate video. But these are two completely different things. And to give you some idea of the totality of the universe, it is estimated that dark energy accounts for about 73% of everything in the universe. Dark matter accounts for about 23% of everything in the universe. And matter, which is the only thing we have any reasonable knowledge of, accounts for a mere 4%. So you can see that on the basis of what we now think to be the case, we have reasonable confidence that we understand 4% of the universe. 96% of the universe is still dark to us, whether it be dark energy or dark matter.